This video is about electrolytic cells. By the end of this video, you should understand how an electrolytic cell differs from a voltaic cell. You should be able to label the parts of an electrolytic cell, and you should be able to perform calculations related to electroplating. Recall that when we started this unit, we divided electrochemical cells into two categories: voltaic cells, which produce current from chemical reactions like batteries, and electrolytic cells, which use electrical current to produce chemical changes. This video will look at the second type, the electrolytic cell. When an electrolytic cell is used, a system undergoes the process of electrolysis. Electrolysis is the process of forcing a current through a cell to produce a chemical change that would not otherwise occur. In this case, we're making a non-spontaneous process happen through the continuous addition of electric current. Some common examples of electrolysis are hydrolysis, where water molecules are split into their elements, hydrogen and oxygen, using an electric current, and electroplating, where one metal is deposited onto another metal. Both of these processes are non-spontaneous, but by adding a constant electric current, we're able to make them occur. Let's look closely at electroplating. Again, electroplating is the process of depositing a metal onto another surface. In the diagram shown here, we're depositing silver metal onto a spoon. Notice that in electroplating, the reaction takes place in a single beaker because the metal needs to be able to migrate from one electrode to the other. When electroplating, the anode will be the metal that you are plating with, in this case silver. We want our silver metal atoms to become silver ions and leave the electrode so they can migrate to the spoon. Therefore, silver must be oxidized to turn the neutral silver atoms into silver ions. The cathode is the object you are plating onto. In this case, we want these silver ions to gain an electron to become neutral silver atoms attached to the object. Therefore, silver ions must be reduced onto the object. Recall that reduction occurs at the cathode. As always, electrons flow from anode to cathode, since electrons are lost in the oxidation at the anode and gained in the reduction at the cathode. We can quantify this process using a few simple equations. The first is coulombs. Coulombs, abbreviated capital C, is a measure of charge, and it's equal to amps times seconds. Amps is a measure of current, so if we know how much current is traveling through the cell and for how many seconds, we can calculate how much charge or how many coulombs have moved through the cell. The idea of the coulomb was used far before we knew about the existence of electrons, so once we know how much charge moves through the cell, we need to convert this into moles of electrons, since this is a value we can then use stoichiometrically. We do this using Faraday's constant. A Faraday, abbreviated capital F, is equal to 1 mole of electrons and 96,500 coulombs. So once we know how many coulombs have traveled through the cell, we can divide by Faraday's constant to convert this to moles of electrons, or Faradays. From there, we can use the stoichiometric ratio between electrons and metal ions to determine how much metal is plated onto an object. Let's look at an example. Here we're told that a current of 5 amps flows for 400 seconds, and we're asked how many grams of silver will be deposited. Let's start by calculating how many coulombs were moved through the cell. Again, coulombs is amps times seconds, so 2,000 coulombs of charge were moved through this cell while it was running. Divide this by Faraday's constant to convert to moles of electrons, and we find that we've moved 0.0207 moles of electrons through the cell. Now let's consider the reduction reaction for silver. Here we see that for every silver atom transferred onto the object, we've transferred 1 electron, since silver ions are +1 charge. Therefore, we have a 1-to-1 ratio between moles of electrons and moles of metal. This means that we've deposited 0.0207 moles of silver onto our object. Now we can simply multiply the moles of silver by silver's molar mass and determine that 2.24 grams of silver have been deposited onto the object. Here's an example to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Notice in this case, our metal had a positive 2 charge. Therefore, for every 2 moles of electrons, we deposited 1 mole of metal. So we needed to divide our moles of electrons by 2 to determine how many moles of metal were transferred. That brings us to the end of this video. Let's review our goals. First, we looked at how an electrolytic cell differs from a voltaic cell in that it uses electricity to produce a chemical change. Then we looked at the parts of an electrolytic cell. And finally, we looked at how to perform calculations relating to electroplating.